In the case of a longitudinal wave, will be different in that we'll have the motion will be going along the same line as the direction of the wave. Consider that you're standing in line to get tickets to something that you want to see. But it's a long line. It has not been moving. At some point, the person behind you, being a jerk, gives you a sharp shove forward. So you're displaced forward. You'll slam into the person in front of you because you weren't expecting the person behind you to give you a shove. And after a moment, you pull yourself back, you're standing straight forward again. It's like, geez, what a jerk. And you think it's done, but the person ahead of you was knocked forward into the person ahead of them. They bounce back. It takes them a second to stable out. Maybe they bounce back into even toward you as they steady out. But that wave, that displacement, moves forward. Now, because the forces involved are basically, I can make this work with impact forces and recoil, then this sort of wave works in all types of matter, not vacuum, because we still need a medium, we still need particles to carry that wave, but it'll work in gases, it'll work in liquids, it'll work in solids. So, let's look and make a graph of, I've changed some of these displacement values to make it work in this case. Let's look at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So, the particle at x equals 0 has a displacement of 0. The particle at x equals 1, actually, what the heck, let's make that an open loop so it stands out a little bit more, has a displacement of 0.8. The part that started it at x equals 2 has a displacement of 1.2. The point that started at 3 has a displacement of 0.8 to 3.8. The particle at point 4 is at this moment at rest at point 4, or it's at its starting location. The particle that started at x equals 5 is at a displacement of negative 0.8, so that takes you to 4.2. 6, that object has a displacement of negative 1.2, so 4.8. 7, negative 0.8 or 6.2. 8, 0. 9, a displacement of 0.8. 10, a displacement of 1.2. 11, a displacement of 0.8. And 12 at rest. So if I look at this, I have areas where the particles are packed more densely together, and areas where they are not. So, well, as we'll see, we'll run across a discussion of this. So this is a longitudinal wave. The displacement's in the motion of the shift. This is, I hope, a useful example to show you how you go from displacement to location in the case of a longitudinal wave. And because the forces involved are just contact forces, this will work in a gas and liquid or in a solid. So if I have a solid, like say the Earth, and I smack the Earth hard with something, like say there is an earthquake. Now, that'll produce transverse waves, waves that move side to side. That'll move out through the Earth. It'll also produce longitudinal waves. that'll move through the earth. The reason why this is an interesting or a useful, I hope, example is that inside the earth, the crust of the earth is mostly solid. The mantle of the earth is plastic, call it solid. The inner core of the earth is solid, but the outer core of the earth is liquid. So, if a very powerful earthquake occurs, then seismologists over a good stretch of the world can detect transverse waves from the earthquake, but some people will be sheltered from that. They will only see longitudinal waves. And everyone on Earth, every seismograph on Earth will be able to detect the longitudinal waves, but not the transverse waves.